Today in this video, we're going to be tackling the Bypass Me challenge from picoCTF 2026. And in this challenge, every time we try to guess the password, the program will sanitize our output and basically strip out any special characters and lock us out. But we're not going to go guess the password, and we're not going to use any buffer overflow. Rather, we're going to be shifting into reverse engineering, where we're going to disassemble this binary, read the raw assembly code, and locate the exact moment where the program decodes the master password in memory, and finally use a debugger to steal it while the program is running. So let's get straight into it. First things first, we have to SSH in. So we can do SSH, and then the format is basically SSH, the username, @ and then the host. So SSH, CTF player, @ and then the host. And we have to specify the port number since it is not the default port of 22 with the -p flag. And then we can get the password here. Yes, and paste in the password. And we are in. So first things first, I like running file on the binary just to see what type of binary it is. And in this case, it is a 64-bit binary, which will be important in terms of the registers and how the binary is laid out. So as mentioned inside of the challenge, we have to use LLDB because we are on a SSH shell, and that is our only tool we can use to solve it. To open LLDB, which is basically just a debugger like GDB, but just newer, we can just write LLDB and then the file. And we can just quickly run the program here just to see what happens. You can see that it's securing modules, running memory diagnostics, all that random jazz. Let's just see what type of passwords we can enter. Let's just type in random characters, numbers, all that stuff. We can see that it has actually sanitized all of the numbers. So what about like if we enter a bunch of special characters, we can see that it just removed all the special characters. So it seems like the program can only allow us to type in letters. So first thing I want to do is disassemble some of the functions. So assuming there's one called main, we can type in disassemble, and then the syntax would be name and then main. And we can see here, this is the main function in assembly code. And this is actually written in AT&T syntax. We can tell by all the % signs. So that also just means that the format is source and then destination. And it's just kind of like the reverse of the Intel syntax, where this is the destination and this is the source. So we're not actually going to read every line. We're just going to quickly scan over for clues. And we can see here that there's a function called decode password. This basically kind of tells us that in this file binary, the password is actually already stored, encrypted somewhere inside of here. And the function has to decode it first before it checks our input against the password to make sure that we enter the correct password. So how functions work in assembly is slightly counterintuitive, where we have to pass in the arguments first. So we can see up here, LEAQ. This basically just calculates the memory address at the base pointer minus the hex of 110. And this basically temporarily saves that address to the RAX register. And this is just kind of like creating an empty buffer for where the password would be decoded into. So now next we can see we have a move Q, and then we're basically moving the RAX into the RDI register. So we're just moving the buffer from up here into the RDI register. An RDI register in 64-bit Linux architecture is basically the first argument to a function. So essentially we have created a buffer space here for a variable, and we moved it into the argument for the decode password function. Once the decode password function runs, it will store the password in RDI, which will be located at RBP minus 110. So now the strategy is we have to go set a breakpoint somewhere here, somewhere inside of the decode password function. So to do that, we can do B or breakpoint decode underscore password. And we can see that it have a breakpoint there. And now let's start running it. So we are currently at the beginning of the decode password function, and we want to basically allow the function to finish decoding the password and then saving it to the memory address of RBP minus 110. However, we don't want to have the function continue after that. What we can do is we can type in finish, and this will basically just get to the end of the function and then pause the execution immediately before the function fully returns. So let's go finish, send that in. So now we are at the end of the decode password function. And now we can assume that the password that has been decoded is safely written into the RDI register, which is basically writing to this buffer, which is located at RBP minus 110. To read what is in that buffer, we can type in expr and then character, since that is what is being stored in that buffer. And then we type in RBP minus and then 0x110. So by running that, we can see that we have a password of SuperSecure. This is the password that was decoded by the decode password and was stored into that memory address. So we can now safely quit from this LLDB debugger. And if we run the function bypassme.bin, we can wait for all the loading screens. And once we have the prompt to enter a password, we can enter SuperSecure. And this should be our password. It'll be authenticating. And there we go. We have obtained the flag. Let's go submit that. And there we have it. So a simple lesson in this challenge is basically never store passwords in plain text, and also never decode passwords directly into local memory. Because if you do, an attacker like us in this challenge could use basic debugging tools to inspect them and simply just extract a password even if we don't know what it was. So if this video helped you learn something new and help you in any way, shape, or form, please give it a like and subscribe and share it with anyone that you think would benefit from it. That's all, and see you in the next one.